So welcome everyone to the SIAM Financial Math Engineering Activity Group virtual seminar. Today it's a pleasure to introduce Sergey Nadtochiy from Illinois Institute of Technology. The talk will be 45 minutes. There'll be questions. Sergey will stop some point in the middle, and there'll be questions also at the end. If you have a question, please, as usual, write it into the chat, and then I'll call on you to ask your question when we take the question break. And then afterwards, if you are available to stick around, there'll be a kind of informal question and answer session with the speaker. And so with that, let me turn it over to Sergey, who will speak on a simple microstructural explanation of the concavity of price impact. Sergey.
Thank you very much, Ronnie, and thanks to all the organizers for inviting me. At least I managed to give one presentation since the quarantine started. So, well, at least I have a chance. I haven't finished it yet. But so I'll talk about this simple microstructural explanation, as Ronnie said, of something that people observed empirically and have argued about for a long time. This is the typical shape of a price impact. I'll explain what I mean by impact and what exactly is that I'm trying to explain. But before I do, I want to give my thanks to people who contributed to this work on different levels. So I had a lot of very useful discussions with Jean-Philippe Bouchard, who helped me understand actually what I've done better than before. And I also want to thank Sebastian J. Mungel, who provided data for the empirical confirmation of the predictions of this theoretical work. And Moise Moyebe was a master's student at the University of Michigan who conducted the numerical experiment, which in fact inspired. So the results of the experiment in fact inspired me for this work. So I could, in fact, it was one of the few cases when you don't do the theory and then test the predictions. You actually see the predictions numerically first, and then you try to build a theory that explains what you see. All right, so let me start by describing what I call price impact and what kind of impacts exist out there. So the heuristic, very general definition of price impact is the phenomenon that prices tend to move in the direction of trades. So if you buy, you move the price up. If you sell, you move the price down. But if you think more deeply about this thing, then you immediately see there are many different variations of this definition, right? So people, for example, identify something called local impact. So if you make a very small trade, how on average does it affect the price, right? So that's local impact. Meta order impact is something that in fact I will be analyzing here, and it's a bit more subtle feature. It's the impact of a sequence, usually a relatively large sequence of co-directional trades. So if you make another small trade, but a lot of small trades, right, altogether, how they will affect the price. And of course, a very immediate reaction to this will be, well, what's the difference, right? They should sum up, right? The effect of every individual trade should just sum up. And in fact, the biggest conundrum, the biggest problem of explaining concavity of price impact is that it doesn't happen somehow, right? The cumulative effect of a meta order is not just a sum of the effects of local impacts, and that's what concavity really means. It's one of the ways in which you can interpret concavity. So I will explain why this happens and sort of provide really an explanation. So it's really not there's no contradiction there. You can make these two be consistent, but it's not a trivial question. Finally, there's another notion of total impact. This is really a correlation between the order flow and the price. And so this is how all the orders altogether affect the price. And this you can measure, and typically it's a linear model is pretty good approximation of that. So that's not something interesting, not something I will talk about here. But you have to keep in mind that impact itself may mean different things. And so the results of this work may not be applicable if you think of different type of impact. All right, so what I mean by impact of a meta order. So there are a few empirical papers that provide data on this. And let me show you one of them. This is from Bakri et al. Paper from 2014. And here you see in rescale units, right, you see the average change in the price from the beginning of the execution of a large number of buy orders in this case, because the price goes up, right? So and this is aggregated over different time periods, aggregated over different securities, and renormalized appropriately. And so the graph you see is like this. And you see that before time 0 and time 1, so 1 is set to be the end time of the execution, you see something that is pretty much linear, but actually at the beginning in a very small region, it looks a little concave, right? It doesn't look quite linear. Definitely the derivative of this curve at the beginning at 0 is higher than it seems to be later on, right? If you think about it. And of course, after this, there's something called market price resilience. I will not talk too much about price resilience, although it is also built into the model that I use for my explanation. And you can see some graphs at the end of my presentation. But typically what happens is after you execute the sequence of trades, the meta order. By the way, meta order is a sequence of trades. So this is what I will, sequence of co-directional trades. After you execute a meta order, price goes back down again on average, right? You have to remember this is all on average, but not fully to where it started, right? So there's a partial resilience in price, partial recovery of the initial price, but only partial. All right, so okay, what kind of, so my explanation is not the first one. In fact, probably it's the last one to date, but so there exists a few more. So let me try to give you a few classes of explanations that exist out there. So the first one is heuristic. I don't know of any rigorous mathematical literature that would use that explanation, but it exists somehow among traders, among practitioners, that this is identifiability of the order flow of the price. So the basic idea is as follows. If you're a large trader trying to buy something, somehow the other traders find out about it and they trade ahead of you, moving the price against you so that it's more expensive for you to buy. And then when they think that you're about to finish your execution strategy, they stop their activity. And so somehow your price, your marginal impact, the impact of every individual trade you make becomes smaller because it's cheaper for you to trade. But the identifiability has a lot of problems, right? The biggest problem, of course, is inconsistent with any sort of market efficiency. Well, say, well, market efficiency also has to, not perfect, right? We know that it only is true up as a first approximation of the market. But there are many other arguments you can present against this explanation. For example, if you're a large trader trying to sell or buy something, it takes time for others to figure out what you're doing, right? So it would be strange if they act very strongly at the very beginning of your execution strategy, when they really don't know who you are yet. They didn't have enough time to detect your activity, right? And then they stop somehow their activity towards the middle, right? At the very least, you should have a period of time where nobody knows yet who you are, right? And so in that case, the impact shouldn't be very high from your trades, right? So there are a lot of things you can kind of come up with to argue against this explanation. Another explanation is coming from game theory, from economics. These are equilibrium models of market makers. And so there are several types of them. So there are two papers that I find sort of very interesting. One has to do with the shape of market makers' preferences. They say that market makers, in fact, maximize not the mean variance, but mean and standard deviation. And that creates certain concavity in the prices they quote and in the price curves. And another one has to do with distribution of size of meta orders. So the idea is as follows. Somehow predatory traders know roughly how many, roughly the size of your meta order, right? So they will know that, okay, at the beginning, you are likely to continue. So they will jump ahead of you, try to trade against you, front run you. And then when they know that you're likely to continue, this is almost the end of your meta order, then basically they stop. But again, how do they know that you have started now, right? That's the question. So there is a lot of criticism of this as well, because this is a very stylized model where there's a single market maker typically against a single client. It's not clear what will happen when we have overlaps of different market makers, different clients starting and finishing. And so that's not really applicable to order-driven markets, to exchanges. Then there's a very interesting recent paper on dimensional analysis, which shows that in fact, if you make assumptions about certain quantities being constant, just to get the right units of measurement for the price impact must be a square root. So not just concave, but square root function of the traded volume. And so that's probably many of you who are interested in this topic, that you probably have heard presentations on this. It's in the paper. And that's a very nice explanation, except that to me, it's not quite satisfactory, because it sort of says that, it says why this must be true, but it doesn't really explain the mechanism by which it happens, right? So it reduces the assumption of concavity of price impact to the assumption of some quantities becoming constant, right? So it may be true or may not be true. And finally, the last explanation, that in fact is the closest one to the one I present here, is the latent limit order book by so I don't list his name, but of course, Jean-Philippe Bouchot is among the authors. And the idea here is that the book that we see in the market, the actual limit order book that contains limit buy and sell orders, is not the complete description of everybody who wants to buy and sell. There are these hidden people who have intention to buy and sell, but they don't post in the limit order book. And if you include them in the limit order book, you will have a V shape. So we have like a linear constant slopes of the book on both sides. So the further you move into the book, the more liquidity you obtain. And so as a result, as you start buying, you go into the book and it becomes cheaper and cheaper for you to buy because there's more and more liquidity as you go. So that's a basic idea. Of course, there's a lot of work to make it rigorous, and there's some PDE results there. And I have to say, and I will come back to this point again, that the two explanations, this one and the one I provide, they in fact coincide in the middle, right? So they sort of start from some different observations, and then they make another intermediate conclusion, which is the same, in fact, in both explanations. But still, I want to stress that my initial point is very different, and my explanation from the very beginning is very different. So what is the advantage of the explanation I propose here? So first of all, I claim I can state it without almost any math. Right, so the way my talk is structured, I will give you the explanation heuristically, purely heuristically, and show some empirical evidence, and then I will go into the model, mathematical model, and I will take questions before I do that. Now, the key intermediate conclusions of this model are easy to verify using only publicly available data. So that's very important because a lot of the papers, first of all, either require the information about meta orders, and this is proprietary information which companies are very reluctant to share. You can pay a lot of money and get it, but your options are very limited. And I know very few sources and very few people who actually have this data, especially on the academic side. And my explanation doesn't require a notion of something that is abstract like a latent limit order book, right? Which we cannot really observe. We have to sort of believe it's out there. So explanation I will give can be tested, at least half of it can be tested using simple microstructural data you can download from everywhere, from many sources, and I get it, for example, from Sebastian. So the model accounts for order-driven markets. So there are multiple agents that trade simultaneously. There's nothing, it's not a stylized model of a single market maker and single agent. And in this model, there's no assumption of inefficiency or detectability of someone's activity. So the agents are not trying to sort of very hard to predict what the other ones are doing, detect who's doing what. This model is microstructural in the sense that I start with economic primitives, I describe them in detail, and then derive the sort of evolution of the price impact curve. All right, so before I promised there's almost no math, right? But I also said I will give you a heuristic explanation. So I'll give you, in fact, two heuristic explanations. The first one is just to convince you that there's no sort of conundrum, no controversy, or no contradiction in having a linear local impact and nonlinear meta impact, right? Remember, I told you at the beginning of this presentation on the first slide, I think, is that you might think that the impact from a meta order is just a sum of the impacts from small orders, from local, from individual orders. And this actually is not true. So how come? So this slide is meant to show you that there are indeed very natural models in which the linear local impact produces a nonlinear global impact or meta impact. And then on the subsequent 3 slides, I'll show you, in fact, why this impact has to be concave. Okay, so 2 different heuristic explanations. So here's the first one. The key statement here, or the key observation, is that we care about expected price impact and not the pathwise impact. So in many models, including, for example, Almgren-Chris model, it's the same thing. So somehow the way that you price, so basically your actions on the price, the trades, will just move the whole trajectory of the price pathwise, right, for every individual outcome. And I claim that, in fact, it's not the same as moving the expected price. Okay, so I want to make that distinction very clear here. So let's assume that X is the price, and let's not worry for now what we call price, because on the microstructural level, there's ambiguity of what is price, but it's some price. And let's assume also it follows some sort of diffusion model, right? And what is the expected price change in this model? Well, if sigma is regular, then the martingale term disappears in the expectation. So the expected difference between xt and x0 is just this integral of the expectation of mu of x. And in general, it doesn't have to be 0, of course, but it may be 0, right? If, for example, your mu has conspires somehow with the properties of the distribution of marginal distribution of x, right? For example, if x is symmetric around 0 and mu is anti-symmetric, odd function around 0, then you can get this expectation is just always 0, right? So this kind of model may create a situation where the price is equally likely to go up and down. There's no trend, right? So it's not a random walk, but there's no trend. And And so it's consistent more or less with what we see in the market. However, now if you introduce a large sequence of co-directed buy orders in this model, right, what's going to happen is, well, under the assumption of linear local impact, every market buy order will move the price by the same amount. So you will get a linear drift. If you trade with the same intensity, the price process will obtain a linear drift upwards. So this linear drift is shown here in red, alpha theta, and your new process, which I call x theta, will evolve as follows. The drift will just change, right? Now, what will be the expected price change in that case? Well, it's going to be the linear part, alpha theta t, and that's what you would expect the total impact to be, right? Just the sum of the individual impacts, linear. But in addition, there will be this expectation of mu of x theta s. And even if the expectation of mu of x s was 0, it doesn't mean that the expectation of mu of x theta s is 0, because x theta is a different process. It has a drift. So the drift that you gave to price has two impacts. The direct, or two consequences, let's say. The direct impact, which is through alpha theta t, this is this linear part that you gave to the price. But in addition, you changed what's inside your mu, okay? And if you think, for example, of mu as just a linear function, try to solve, this will give you a differential equation, in fact, which you will solve, you'll get exponential behavior of the mean, right? So immediately you see that even for very small choices of mu, for very, very specific simple choices of mu, you can get nonlinear, and in fact, if you like it, you can make it concave, right, impact on the price. This is just a basic sort of explanation of that conundrum I mentioned at the beginning, that in fact, if you realize that what you're measuring is expectation, not the pathwise impact, then the local impacts don't have to just sum up, right? There's a nonlinearity in the middle there coming from the drift mu. This drift mu will be important to my model. For now, I don't want to say what it is and why we need to have it, but if it's there, I hope it's clear now that there is no contradiction between having linear local and nonlinear global impact. Maybe I should stop for a second at this stage too, just to take questions if there are any.
There are no questions in the chat. Does anybody want to type something in the chat? We can give it a minute while you stop. Yeah. So Agostino, go ahead.
So, question, Sergey. How should we think of the modified process x as theta? Because I can view alpha theta practically corresponding to some sort of permanent price impact.
It is, exactly.
Right. But how would I think of x t theta? That's this new process that incorporates the rate at which the orders have been executed.
So this is the affected price. So x was the unaffected price, and x theta is affected price.
So it's like as if x is the fundamental and x t theta would be the...
What happens after you start trading?
Mm-hmm. X
is what happens. Yeah, so x, you should think of x as the law of the, is the unconditional law of the price process. And x theta will be the conditional law of the price process, where you condition on the fact that you are executing at rate theta.
I see.
So basically it's affected price versus unaffected price.
Yeah, thanks.
Sorry, yeah, go ahead, Agostino.
No, thank you, Sergey. Just wanted
okay, sure.
So just to follow up, I assume, Sergey, when you go to the data, you assume you observe x theta, but you don't observe x.
The opposite, in fact. So in fact, I cannot see x theta because I don't have meta orders. So maybe I should clarify my statement about verifiability of the predictions of this model. In this model, I'll make two predictions. Both are important, but somehow only the first one, the first one is more questionable than the second one. And the first prediction has to do only with x. That's the interesting part, not with x theta. From x to x theta, you can go more or less by logical arguments. Even though you're right, there's still something to be verified using meta orders. It's just less important, let's just say. The sort of verification about the information about x theta will be less important. Yeah.
Okay, any other questions at this midterm stage?
All right, so let's continue then.
Okay.
So I just hopefully convinced you there is no problem having local linear impact and non-linear global impact. Now I want to convince you that there's something to do with concavity, that why this impact would be concave, this expected meta order impact. Well, so here's where notion of stationary density or stationary distribution becomes important. So I still call X the price, but now I want to be a bit more careful. I want to acknowledge the fact that we look at microstructure of the market. And of course, we don't observe X, right? What we do observe is bid and ask prices. And the notion of a price is questionable, but it's natural to assume that the true price lies between bid and ask. And under the additional assumption that your bid-ask spread is always equal to 1, I get this this conclusion that the ask and bid prices are the roundings of X. So this first one is the upper rounding, this is the ceiling, and this one is the floor. So in fact, the observed prices would be the roundings of the price X, fundamental price X. And so far I make no other assumptions on X. Then let's assume, as before, that there's a linear local impact on X. So a buy trade of size delta will move X to X plus alpha delta. So alpha will be the magnitude of the impact, delta is the size of the order. The observed impact, right, will not be on X, it will be on the mid price. Okay, so it's what? For example, we can take the ask price after the trade minus the ask price before the trade. So it's the rounding, it's a nonlinear. There's another level of nonlinearity coming up here, right? So of a different type for now. I will merge the two in the middle of my presentation, but for now they are different. Then what is the marginal expected observed impact of that particular trade? Well, it's the expectation of the previous quantity, right? Of the change in the observed mid price, right? You take the difference in mid price. Sometimes it will be 0, right? But with some probability it will move, right? So the price may be moved by a single trade. Now, if you think about this expectation, what does it depend on? Well, here, because everything is done with a rounding operation, in fact, all you care about is just x0 modulo 1, right? So you can, I mean, and that makes sense, right? Because in the market, you always see the bid and ask. And if the difference between them is always 1, then the only ambiguity is where exactly x is between bid and ask. So you can always take x modulo 1. You only care about the fractional part of x, right? That's the only random thing there. And so this expectation can be done with respect to the distribution of x0 mod 1. Now, let's assume also that the alpha times delta is very small. So the trade is very small. Then if you think about this expectation, right, most of the time, in fact, it will be 0, right? Because for most of the values of x0 will be between 0 and 1. And if alpha plus delta is very small, then it's not, you're not going to cross across 1. So the only way this can change is if you're very close to 1, right? So this is the only way this difference can be positive, right? When x0 is very close to 1. So then this whole expectation in this asymptotic regime of small delta becomes just determined completely by the typical distribution of x0 mod 1 at 0.1 minus, so the left limit of 1. Okay, I want to stop for a few seconds to digest what I said. That this expectation really, asymptotically, when delta is very small, depends only on the value of the density of x0 modulo 1 close to 1. Because only when x0 is very close to 1, this is when your single trade can push the price across the digit and change the observed price. Otherwise, you don't change anything by a single trade, right? All right, so that's the first observation. Now, what can we say about this typical distribution of x0 mod 1? Well, clearly, when I say typical, I mean stationary, right? But stationarity, to get stationary distribution of some sort of process X, I need to know a little bit about dynamics of this X, right? So I want to argue that X has to have special dynamics. In particular, X has to have a special drift, okay, drift of a special type. Now, why is that? Now, this is where a little bit of modeling comes in. Now, remember that X is a fundamental price. And think of X for now. And in fact, in my empirical experiments, X is always the so-called micro price. It's a weighted combination of bid and ask price, where you weight everything according to the volumes at the best bid and best ask. And this quantity X is very well known to be a good predictor of the direction of the next market order. So if it's close to, if X is very close to the ask, in other words, very close to 1, then the next order is likely to be buy, and vice versa when X is small, close to bid. Okay, but in fact, you can argue that any notion of the price must have that property. The price must be a predictor of the next order, at least the fractional part of the price. So if X approaches 1, it means the market is about to go up, right? Which means the next order should be likely to be buy. and vice versa if X is low. So we make this assumption, or if you think, if you like, you can think that we assume that X is a microprice, that X predicts the direction of the next trade. Okay, but then what happens as X moves up a little bit? If X moves up, the next trade is more likely to be a buy, but the buy trade has a positive impact on X, so it will move X even further up. So you have this feedback loop, and once you resolve this feedback loop, you get a process X which has a drift that pushes this process away from 1/2. So I claim that the process X must have a drift that is such that it's positive above 1/2 and negative below 1/2. Typically, it's something like X minus 1/2, so something like linear function that is 0 at 1/2, and if X is above 1/2, the drift pushes this process further up. If it's below, then the drift, then X is pushed further down. Then how does a stationary distribution of such process look like? Well, if your mass is always pushed away from 1/2, you're going to have a U-shaped distribution whose mass is the smallest around 1/2 and the highest at the tips at 0 and 1. Okay, so that's a simple logical chain that gives you this kind of pictures, right? So here I look at the stationary distribution of my process X, the microprice, modulo 1, right? So I only look at the fractional part of the microprice. In other words, I'm basically looking at the imbalance, at the limit order imbalance. All right, and my logic, the chain of arguments that I presented here, and just to remind you, is that because of this feedback effect of X on the price and X on the trades and trades on X, the correct model for X must have a drift which pushes X away from 1/2. And this in turn, and you can prove it, and it's proved in my paper, that this leads to stationary distributions which are U-shaped, where the wings are the highest points and the middle is the lowest point. And guess what? If you try to estimate these things, and it's very easy to estimate this from data, that's exactly what you get, right? You simply have to look at the fraction of times that you find your X in each bucket. So you split your interval from 0 to 1 in buckets. You try to find where X is and try to find the fraction of times that this happens, and you will get this kind of shapes.
So Sergey, there's a question that you might want to take now before moving.
Yeah, okay.
So Priyanshu, do you want to say your question? Priyanshu? So maybe I'll say it in the interest of time. So,
sure. So
Priyanshu Ahuja asked, what is alpha exactly? And if X is an integer, then ask and bid are equal. How does it add up?
So I guess I have to go back to this one, right? So Renu, you got interrupted for the beginning of your question. Can you repeat the beginning?
What is alpha exactly?
Alpha is the coefficient of the permanent local linear price impact. So it's like lambda in the Almgren-Kris, right? We don't do any temporary impact, just the permanent. It's a coefficient of linear permanent impact, which locally happens. So we are actually in the Almgren-Kris model, if you wish, right? Without any temporary impact, any transient impact, but with additional feature that, two features, that the process X has a drift, and that's the key feature, in fact. And another less important feature is that we measure impact not on the fundamental price, but on the observed price. But in fact, that's not so important. The most important part is that you have a drift there, which is not zero, non-constant.
And is it correct to say that because X is an integer, ask and bid are equal?
X is not an integer, no. The roundings, that's why we take roundings, right? So X is something that moves in continuous time. So X is not the bid or ask price. It's a micro price, if you wish, right? So micro price moves much faster than bid and ask, right? Because the limit orders are adjusted to the much higher frequency than you see trades or you see changes in price. So X we view as a continuous time process, as a diffusion. And the bid and ask prices, they change less frequently. They are the roundings of X. So they are integers. So for example, I don't know, so I share my screen. You must see my my pointer here. So ask and bid, right, are given by roundings of X, but X lives on R, right? It doesn't live on Z.
Okay, thanks.
All right.
Thanks a lot. The question is answered. Perfect.
Okay, great. Yeah, sure. So that's what you see. There's a bit of a caveat to this. Let me maybe mention it now. So these pictures are produced by measuring everything on business time. So in fact, when I say fraction of time that you find your process X at each bucket, what I mean is a fraction of volume that is traded while X is in the bucket. So everything I said is correct, but you have to replace time by business time. And so that is something you just observe empirically, right? It's consistent with the model. And I don't want to sort of emphasize this too much. So for simplicity, if you like, you can just forget about business time, just think of regular time everywhere. But you have to remember that when you actually empirically compute all this, it's about business time. It's not about actual time. All right. Okay, so that's another set of couple of stocks, and you see very similar phenomenon there, right? So I just told you how the station distribution looks like, and the fact that the marginal impact of your trade, you see your first trade, has to do a lot with this shape, and in fact with the wings of the distribution, so how this distribution behaves. And remember, the wings are this part. So this part is important for the buy orders. This part is important for the sell orders. And in the paper, there's a theorem, and I will show it to you, that connects this precisely. But then again, why concavity? Where's concavity coming from? So I have to show you now, to prove concavity, that throughout your meta order, the wings of these distributions will in fact go down, right? This will mean that the initial impact you make will be higher than any subsequent impact, right? So again, think of this wing as really being equal to your marginal impact of your single buy. Then if the wing keeps going down, it's not clear what it means, right? Because it's stationary distribution, but okay. If somehow keeps going down as you keep measuring this distribution of your X, if the wings go down, then your impact goes down, okay? So let me try to argue that this happens. Again, without mathematics, or without too much mathematics. Okay, so if you submit a long sequence of buy orders, what you're gonna do is you add a drift to X, right? So hopefully there's no doubt about that, right? We talk about linear impact, right? So drift that you add will be alpha theta dt. Now, let's now imagine, for the sake of the argument, of course it's not realistic, but just imagine that theta is very large. And theta is your participation rate. It's how fast you trade, how fast you buy. And let's imagine you buy really fast, right? Then this theta, this drift, is going to dominate the initial drift mu that your process X had, right? So really you're going to think of, but remember now that we're looking at X mod 1. So it's this new X modified with theta, but also modulo 1. So it's like a diffusion running on a circle. Now, if you take a Brownian motion and you add a huge drift and you run it on a circle, what would be the stationary distribution of this process? It's going to be uniform. Because the Brownian motion doesn't matter anymore. The drift doesn't matter. Only this constant drift that you add will matter, right? So what it means is that this U shape, if you wait for a very long time, if you start your meta order, you wait for a long time, the distribution of your X will actually converge to something that is constant. But the constant, right? Whereas the U-shaped distribution must have wings above 1 because it's U-shaped. So immediately, necessarily, your impact has to go from something that is strictly above 1 to 1. Ultimately, at the end of your meta order. So when you converge to the new stationary regime. And of course, it's only true for theta that is very large, right? And it's very unrealistic. But in fact, it turns out it's true even for small theta under some assumptions on the model. And that's a non-trivial result from the paper, which requires a little bit of mathematics, which you just have to trust me is true. I don't have time to present the proof, but you can find the proof in the paper. So it's not just true for very large theta. In fact, it's true even for very small participation rates. All right, so I think that's another good point to take questions, because from now on, I will be explaining the model basically and how exactly all these things can maybe made rigorous, right? And how one can compute things in this model and so on.
Okay, so there's a question from Martin Larson. Martin, do you want to say it?
Sure, Sergey, I was just wondering about the figure on the previous slide.
Sure.
And the x-axis of that. I thought it would be between 0 and 1. If your process x mod 1 is between 0 and 1.
So there will be there will be 9 here. So yeah, okay, so the axis is completely messed up, you're right. So yeah, it should be points. So yeah, it's not 0 to 0.2, 0.4, 0.6, 0.8. Yeah. My bad. Yeah.
All right.
Good point. Yeah, so it's between 0 and 1. You're right, absolutely. Yeah.
Any other questions at this stage? Okay, so we have just about 10, 12 minutes left. Sergey,
okay, but that's fine. I mean, so in fact, the math is the least important part of this presentation. So pretty much I've delivered all the messages. But still, let me try to go briefly. In 4 slides, I'll try to explain the model, of course, with a lot of gaps. And so, oh yeah, by the way, maybe a few words about what happens in this model before I even give you the model itself, give you numerical results, right? So you saw these pictures of U-shaped distribution. So how does this distribution look like in my model? Well, here's how it looks. So you have a sequence of pictures. You read them from top to down, from left to right. So first, second, third, fourth. And across these pictures, what you do is you increase your theta. So you look at the process which is affected by a trading rate of size theta, and you start with theta equals 0, and then increase it, increase it, increase it. And so what you see is, of course, the wings go down. So first you start at 6, then you go to 4, 2.2, and then 1.5. So ultimately they will go down to 1. But on top of that, you see something interesting, right? You see symmetry being violated, right? So it's not just the wings going down. In fact, the mass of this distribution, the center of mass, moves to the left. Now, what it means is that the expected value of X modulo 1 will decrease. Now, if you remember a definition of a microprice as a weighted combination of bid and ask, it means that there will be, in fact, more limit orders on the ask side than on the bid side. So the ratio of the ask limit orders to the bid will increase. If you are buying, it's very good for you, right? It means liquidity actually improves for you throughout the execution process. So as you as you add theta to the market, something strange happens. On the one hand, you move the price up, so you do bad for yourself. On the other hand, purely mechanically, in this model, somehow without any strategic behavior, the agents choose to post more limit orders on the ask side of the book, which is good for you. So liquidity improves on average throughout the execution process. And that's something that is consistent with the prediction of Bouchard's model. And it's also consistent with the observation of some practitioners I have talked to about this, that in fact, it's not just the wings. In fact, the whole X gets, the whole distribution of X model 1 shifts, and it translates, if you think of X as a microprice, translates into improved liquidity throughout the execution process. All right, so that's just a side remark to connect this result to other models. Okay, so what is the model? I can do it very quickly. I think 5 minutes should be enough. The model starts from my previous results with my student back in the University of Michigan. Those are very theoretical models. We got very deep into very abstract things, but turns out that the core modeling modeling framework is very important here, and it's very simple, in fact. So we think of a market where market orders arrive, potential market orders arrive according to a Poisson process, and we know that's not true. Market orders do not arrive according to Poisson process; they are clustering. That's why they call them potential. So the actual how is it determined whether potential market order becomes a market order or not? Every order comes from an agent. An agent has a reservation price. And this price, we think, is the fundamental price, this price X, plus some sort of adjustment, Xi. Xi, you should think of it as a noise, something zero mean IID. And a market order becomes an actual buy order if this reservation price, P, becomes above the ask price. Because it means the agent who comes with the intent to buy he prices the egg below the most he will see, right? Makes sense. So you put all together, okay, and denote by F the CDF of Xi. Turns out very tractable, nice model.
So Sergey, your sound is going in.
Make things even more, avoid a lot of complicated notation and all that. I take an infinite activity limit, right? I take a limit as the intensity of the Poisson process goes to infinity, but the size of every order goes to 0. Okay, is it better now?
Yeah, I think it's better. If you maybe want to turn your video off for the last few minutes, that might make it just be safe. And then we'll put it back on at the end.
Okay. Say again, Ronnie?
Maybe if you put if you're having trouble with your connection, maybe you want to put your video off.
Yeah, okay, let me do that.
Let me do that. And then put it on at the end.
Yeah, so okay, so I put it, okay, so maybe it will help. Let me know if it helps. Okay. All right, so yeah, all right. Okay, so as the intensity of the Poisson process goes to infinity and the size of each order goes to 0, you can get in the right scaling, you can get a limiting model, which is diffusion model for the for all the related quantities. There are 2 main quantities we care about: the X, the fundamental price, think of it as a market as a micro price, and the total trade volume in the market. And the volume here is given by this expectation of a function, the CDF of this psi applied to x. And it's not so important what this function is really. What is important is that what's inside the integral becomes higher if x approaches the integer. So when what people like to trade with certainty, so they will be sort of trading more if x is close to 1 or close to integer, any integer, and it's not really a monotone. So in the end, the trade volume will not be monotone. There will be spikes and values and so on. Now, what about the equation for x? Now remember this feedback loop that I described before, that v is affected by x, right? Because as I just mentioned, the intensity with which people buy or sell depends on where the price is. But also x is affected by v, right? Because there's a price impact. So if a trade happens, x is moved. And so if you resolve, and this is where I skip a lot of derivations, of course, but if you resolve this feedback sort of dependence, you get an explicit formula for the dynamics of x. And it turns out to be diffusion exactly of the form that I described earlier in this presentation. And what's really important is the properties of this function mu. It turns out that mu and sigma are both one periodic, so there's no sort of, so mu is given by this expression here. But again, since it may be hard to visualize, let me list the properties. Mu and sigma are one periodic, sigma is even. So again, sigma is not so important here because it's you are largely allowed to assume what sigma is, right? So it's not so important. But mu really is forced. The properties of mu are forced by the economic assumptions you make on the model. And in particular, it's odd with respect to 1/2 and increasing on 0, 1. So think of mu of x being equal to x minus 1/2, okay? Modulo 1. So everything is periodic from 0, 1 on, okay? And as I described before, in this x, it makes sense that for such x, the stationary distribution will be, in fact, U-shaped. Okay, now how do we measure impact in this model? We assume a VWAP executor who trades proportionally to the overall order flow, right? So theta will be theta. So theta times v, where theta is the participation rate. Now, how does the executor measure the expected impact on the mid price of her meta order of total volume V bar? So V bar will be total volume. It will be split into small pieces. All those small pieces will be submitted to the market. And then we look at the trajectory of the price impact, how it varies, right, up to level V bar. So she looks at the previous execution intervals in some sample of size L, records the changes in the quoted prices over each interval, computes the sample average. And mathematically, this means that she takes an expectation. She takes an expectation of this difference, right? The ask price at the end of the execution minus the ask price at the beginning of the execution. Right? So when I take expectation with respect to theta, I emphasize the fact that this is a conditional expectation. And again, I don't have space here to go into details of describing what it means, but basically you're conditioning, and this goes back to Agustino's question, that your expectation is not overall expectation. It's of a subsample where you are known to trade, to buy with rate theta. Okay, so that's the conditional, this is E theta here. And how do you determine this initial and terminal time tau 0 and tau 1? Well, we assume here is that the initial time of the executor is uniformly distributed across all her trades. So basically when she picks the initial time for the sample, she picks it completely at random. And one way to describe it is to take this inverse of her order flow applied to some uniform random variable eta. It's just the same as saying the initial trade is equally likely to be any of the trades you made in the past, right, in the sample. Okay, and the terminal time will be the time when you reach your target, right, when you reach V bar. Okay, so that's this formula. There's some mathematics, behind it, which I skip, but okay, I think this should be enough. All right, so, and I here above the slide, I repeat the same formula. Okay, now what happens when the sample size goes to infinity? Now, it turns out, because of this form, it may be easy for you to guess that the limiting expression for a large sample will have to do with the price X run on the business clock, because here, everywhere, you see this inverse, right? So everything is run on the business clock. And that's why I mentioned those pictures at the beginning, in the middle of my presentation, were constructed for a process run on the business clock. And it turns out, and you can compute everything using ergodicity theory, that if you take L to be infinity to infinity, you get the following expression for your I. So your I is really the integral with respect to the stationary density of your unaffected process. So X hat is the price run on the business clock, but without the execution, so unaffected by theta. And what you compute here is the expectation of the ask price at the terminal time, V bar over theta, right, of the affected price run on the business clock, -1 and so on. And here we have a nice expression. Well, I don't know if it's nice or not, but it's very similar to what we've seen before for this affected price of the affected price run on the business clock, x hat theta y. So it starts from y and has additional drift theta, which appears here, right? And in fact, what matters here is that not the specific formulas for mu hat, but the fact that mu hat gets skewed. It's no longer symmetric because you add a drift to it, right? You can think of it as as if you added a constant to something that was symmetric against 1/2. And so so the symmetry is ruined. So the typical stationary distribution of this process set will no longer be symmetric when theta is not 0. Okay? And that's when you lose that U-shaped property. All right, so what about the main result? What about asymptotic concavity? How from all of this we can conclude or verify that the impact is concave? Well, so here I just repeat the formula from previous slide. This is how your impact looks like. It's a function of the total volume traded, V bar, a function of your trading rate, theta. Okay, now psi is the stationary distribution of the unaffected price. So x theta with 0 means that theta is 0. So you when there is still no theta, and then you shift the regime, you change the regime of the market, and X obtains the drift theta. Okay, so it turns out, and this is a theorem in the paper, that you can connect the marginal impact, so derivative of this I with respect to V bar, so there's a type of this second V bar should be 0, by the way, I apologize for that, at 0, so initially, when you trade a very small quantity, your impact, marginal impact, turns out to be alpha times psi at 1. So that's exactly what I said. This is the wing of this distribution that you get. And as the volume V goes to infinity, so at the end of your execution for very large quantities, in fact, your marginal impact becomes alpha times psi at 1. But psi is the stationary distribution of the affected process, x hat theta. Okay, so this explicitly connects the marginal impact to the stationary distribution of two processes, one with theta 0 and one with your theta. All right. You start with a process that is not affected yet. So the initial impact you experience is coming from the overall dynamics of the unaffected process, and at the end of the execution, you experience the impact that is coming from an affected process, affected by theta. And these are the two main results of this work, really. So under certain assumptions on sigma, namely symmetry, psi is U-shaped. So indeed, what you saw empirically in the previous pictures is correct, and theoretically is sort of justified. And of course, if it's U-shaped, then psi at 1 has to be above 1 because the middle has to be below 1, right? So then the wings have to be above. And if you make additional assumptions on F, something like log concavity, for example, then you can prove that this conclusion here is true not only for very large theta, but in fact also for So forget you can just prove that in fact even for very, very small theta, the stationary distribution phi, which is the stationary distribution of the affected process, is in fact decreasing in phi, right? So it means that when theta is 0, phi equals psi. They are the same, right? So when theta is 0, the wing of this phi has to be above 1, as we know from this statement. Now, if you know the derivative is negative, it means that for very small theta, the wing of phi has to be below the wing of psi, right? So it means that indeed, for very small participation rates, your terminal marginal impact will be lower than your initial marginal impact. That's really what it is, right? And that's pretty much all. So I explained the ideas heuristically. I showed some empirical justification of what's going on, and then I gave you a model where I skipped a lot of mathematics, but indeed I showed you the main result, how they sort of come to be. Maybe there is one more thing to show, that in this model you can also compute resilience if you want, but you know, there's not much to say. It's just to sort of show you that in fact it looks kind of what theoretically is predicted, that this is a computation of predicted impact in this concave, as you see, and this is a computation of the predicted resilience. And if you look at the numbers, you see that the price doesn't go down all the way where it came from, right? Because here the difference is 0.25 and it goes back down only by 0.12, right? So you don't have full recovery there. So you do see what you might see empirically, judging by the first picture I showed you at the beginning of the slides. All right, so that's all. Thank you for your attention. I hope I was on time, and any questions are welcome.
Yeah, more or less. Thanks, Sergey, for an interesting talk. Now for the heated discussion. So Agostino, you want to go first?
So Sergey, thanks. I think this is a very interesting talk. I have a question when you mentioned the liquidity. You said that essentially, if you have a lot of buy orders that are accumulating on the limit order book, then this will translate into higher liquidity, which is consistent also with the existing theory of Bouchot and so on. But then I'm also thinking that if you have a lot of buy orders, then you have a lot of asymmetry between the sell side and the buy side of the market, which should widen the bid-ask spread. So here we are thinking of a different dimension. You're not thinking about bid-ask spreads. You're thinking more about pricing. Is it correct?
Yeah. So absolutely, yeah. So Agostino, there are. So the first assumption we make is that whoever implements this execution strategy doesn't go nuts and doesn't really sort of trade so fast that the bid-ask spread changes. But you're right in saying that bid-ask spread has a lot to do, and this is an assumption that is very crucial here. So to emphasize this, I want to show you the pictures at the end. So this is what you see if you try to recover U-shape for stocks whose spread is varying a lot, which is not fixed to be one. It doesn't matter so much what this is, what the spread is. What matters is it doesn't change too much. But usually, if a spread is large, then it changes, right? So it's not, it varies much more. And so it's true. You're right that when the spread is varying, you get another variable which affects your impact, right? For example, maybe you have a very favorable limit or imbalance, but the spread is very large, so it's going to narrow, right, very soon, and that's a factor we have to take into account. So, and this is not taken into account in this model. So the assumption I make about a single constant spread, effectively it means the spread is just a single tick, right? That's crucial. Yeah. And and that's why. Maybe to go back to a question, right? That's why I claim that this picture of shifted imbalance, if you wish, shifted liquidity, that's all you need to know to sort of to argue about impact, right? If the spread is also there and changing, then it's a different factor, and it has additional information which is not here.
Yeah. Perfect. That answers my question.
Okay, good.
Other questions? Okay, Sebastian. Yeah, Sebastian, you want to go ahead? Let's go, Sebastian, then we'll come to you, Mikhail.
Hi, Sergey. Could you once again, how does resilience appear in this model?
So I didn't discuss it at all, for sure. But okay, let me just maybe, because it's not.
It appeared in the end in some of your graphs plots in the end.
Yeah, you're right. So you can compute it, but it wasn't discussed as a part of the model. But what happens is, you can imagine, right? So let's just it's easier to visualize things. So you come to the market at random time. You observe your X, your imbalance, at a random point, right? And it's distributed according to station distribution of X. Now once you start trading, you change dynamics of X, right? You add a drift. And now think of it, now you have a new dynamics, new diffusion process, which starts from a non-stationary distribution for itself, right? So its mean will move because the distribution it will converge ultimately to its stationary distribution. And this mean will move, right? So you'll be in a different regime as you keep trading, because now you have a different process. And at some point, you stop, right? And now you are at the stationary distribution of the affected process, but the true dynamics become unaffected. So it's, again, you start the old diffusion now, but from a stationary distribution of the new diffusion you created, right? And then, of course, you can imagine that, again, there will be an adjustment, right? Again, that marginal distribution will converge to the stationary distribution of the old process, which will create a change in the mean, right? So that's basically what happens. You basically shift between two diffusions. You start with one, and then you create another one by your actions. But because of that, the distribution of X changes, adjusting, becoming stationary distribution, and then you start again from that and move back to the old diffusion. And so your marginal distribution also moves back to the marginal distribution of the old diffusion. Yeah. Okay. Thanks.
Sebastian, do you want to go next?
Yeah, sure. Actually, just to tie in a little bit to Agostino's question, when you showed some results for stocks that were not always, or not typically one tick, these guys. And you get this sort of very bizarre shape for this extracted stationary density. But what if you measured it relative to the spread? So instead of measuring price on an absolute scale of 0 to 1 from the bid to the ask, you measured from 0 to 1 whenever you go from bid to whatever ask happens to be. Do you think you might recover the?
Oh, that's adjusted. So you're right. So this is adjusted. So basically, what I do is I rescale.
So this is already rescaled.
This is already there. Yeah,
okay,
yeah. Otherwise, it wouldn't make any
it's
sense. You're right.
Okay,
Yeah.
so
Otherwise,
it's just garbage. It's just garbage anyway. Yeah, even after rescaling.
Yeah.
Okay.
But I have to say, maybe it's just I don't know if you would ask another question, but I'm still not convinced. Maybe if you take more data, maybe it will be better, because for those stocks you have also they happen to be less activity, like they happens to be less data for that. So yeah.
Yeah, and something the actual question I wanted to ask was more about the reservation price. So if you go back, I guess where is it? It's around slide 14 or so. That you
find it. Yeah, just a second. Sorry. This is.
No, that's too far back. Yeah.
Yeah, right here. Mm-hmm.
Yeah. So what role does the density for this reservation price play in the results? Like, does it affect in some way the slope that you see at the two ends of the stationary distribution? Or,
you're right. It actually has a very non-trivial result. That's why I doubt to say anything definitive. It definitely has a strong effect on what you see, but I cannot really give you intuition, right? Exactly. So okay. So I can say in general why it's important, what it does in the model. Translating it immediately into price impact, I don't know, right? But okay. So where it's important is that, remember, there's this feedback loop, right, between V and X. So X is affected by V, but V is affected by, so the way V is affected by X is exactly through F, right? Because of this spiking. So what's important in this model is that the actual orders, they are not uniformly distributed in time. So that in fact, when X is very close to the integer, you get more orders coming in. Okay, and that's actually important. But again, I cannot say intuitively why this is important for the, I see it on technical level.
Yeah. It's very complicated.
Right. But this basically, but basically, if you look at mu, right? I don't know if you see formula for mu. Mu is function of f, right? So maybe that's a bit. So what is really crucial? Okay, maybe one thing I can do. So I can say, mu is crucial for the U shape, right? The shape of mu. So that mu is basically increasing function, which is 0 at 1/2, right? And that you get, and mu is in fact explicitly given here on this slide by f, right? So it's basically. Well, it's hard to describe it, but you can imagine if f becomes very, very flat, the effect of mu becomes less pronounced, and you have less of a U shape there, right? You have more like wings go down. So maybe on this level you can, but it's not a monotone dependence. It's not some sort of a. So it's easy to express, but it's the effect of f on mu is explicit, and you can test different versions and get different results for the impact.
So maybe
okay, great, thanks.
Maybe one last question, Renee. Do you want to say a question?
Yeah, how was the first plot computed? What stock do you aggregate? How many days? I mean, how can you get this beautiful concave and then relaxing curves?
Oh, you mean the very first, this one?
Yeah, you compute expectation. How are these how is this expectation actually computed?
It's very difficult to understand. So so this is a paper I can send you. I can send it to you.
I've seen it before, but I want to know how is it practically.
The short
computed?
answer is I myself don't completely understand it, because the details are not all there in the paper, and it's true for almost every other paper which contains graphs of this concave impact, right? So what they do is they take proprietary data on different assets of the same company, on different assets, executed over different time intervals, over different volumes, and then they appropriately rescale everything so that it should make sense to put them all in the same picture. But when they do this rescaling, there's a lot of questions to be asked, for sure. And I myself was never happy with this. It's just something you have to put on a slide to say. But really, I mean, you talk to practitioners, and I mean, again, my personal impression is they all say, we don't really know exactly if it's concave, okay, but we need to have some model. And it's just too difficult for us to estimate it. So if there's a chance it's concave, it's concave, but it's definitely not convex, right? That's what they'll tell you. It's definitely not convex. It could be linear, could be concave. We don't know, but hey, why not concave? And in these papers, all of them, all the ones I've read, they are all subject to criticisms that you don't exactly, you can always say, hey, these two are just computed at different rates. Why would you put them on the same plots? For example, your execution rate for one asset could be different than for the other. They rescale and then they match everything so that the execution time is the same. And they put all these curves together, they sum them up with some weights. And you can criticize all of this construction at every single step, but that's just all we have.
Okay. Yeah. All right. So that's we're out of time. So thanks very much, Sergey, for a very interesting talk. Let me see a couple of announcements. The next talk in this SIAM series is September 17th, 2 weeks from today, by Renee Carmona. And in the alternate weeks, the Bachelier Finance Society talks, I believe, are restarting. Okay, so thanks everyone. Thanks, Sergey, and feel free to stick around for further question and discussion if Sergey is available as well. Thanks.